Hello and welcome everyone to this new video that we have here under the Steel Design series here in the Online Engineer. Please don't forget to like our channel and subscribe so that you'll be updated for our new videos. Now, for our topic for today, we're going to discuss steel design and compression members. If you haven't seen our video on flexural members, please visit our channel and watch this video so that you will learn about the mechanics involved for flexural members and also the NSCP 2001 provisions that we are going to apply. All right, moving ahead with our topic for today. Let's now have a look at our short discussion. So we have here buckling. As long as a column remains straight, it can be analyzed by the methods of simple stresses. Maybe you're familiar with the simple stress F equals P over area. That's all we really need if our column is straight and it could just simply carry the load that is applied onto it. However, if a column begins to deform laterally, when we say laterally, it will deform, it will bend on its side. Most of the time on its weak axis, the deflection may become large and lead to catastrophic failure. This situation is what we call buckling. And this can be defined as the sudden large deformation of a structure due to the slight increase of the existing load under which the structure had exhibited little, if any, deformation before the load was increased. All right. So what happens when there is buckling? So you can see here on the picture on the right, this is what happens. As you can see here that there is a deformation, all right, on its side. This is what we call as the lateral deformation, and this is known as the buckling phenomenon. If the compressive load P is less than the critical load, which later on will be defined in our next slide, as well as the equation that we're going to use for determining the critical load, then the column will remain straight, as what you can see here on our left figure. And it will shorten in response to uniform compressive axial stress, as what we have mentioned earlier. That's simply P over area. It follows tension stresses, compression deformations, and so on. Those formulas and principles that we have learned in strength of materials. As long as P is less than this critical load PCR, the column is in stable equilibrium. So once again, this condition over here, this is P less than PCR. Analysis will just be using simple mechanics, strength of materials. P over A, and probably the deformation, we have PL over A, if you still recall those formulas in strength of materials. However, when the compressive load P is increased to the critical load PCR, the column is at the transition point between stable and unstable equilibrium, which is now called neutral equilibrium. So it's now under this condition. This is now P equals PCR. As you notice, there is now some buckling going on over here. It's bending onto its side, and just a slight increase of the force that we have here, and this column will be on the verge of collapse, and it will start to fail, and the entire structure will fail. All right? So this is the case of P equals PCR. It's just at the point when the structure is at the transition of being stable and unstable. Okay, so that's the condition that we have over there. Now, let's define some of the formulas that we were going to apply for the analysis of compression members in steel design. So we have over here the critical buckling load formula. That's PCR equals pi squared EI over KL squared. All right, we are familiar with E, that's the modulus of elasticity. I is the moment of inertia. K is the effective length factor. And of course, L is the unbraced length of our member. All right, that's the formula, pi squared EI over KL squared. If this is in terms of load, then we can also express it in terms of stress, simply dividing PCR over our area. PCR over A, we simply copy this formula over here, and we include the area. All right. Now, this I could be expressed in terms of the area and the radius of gyration. So what you can see here, the radius of gyration is actually square root of I over A. Or, if you're going to rearrange this term over here, you can express this I, in terms of A and R, so that it will now be pi squared E, this I here becomes AR squared, okay? All over KL squared times A. The area will cancel out present in the numerator and denominator, and we are left with this form of our formula. And we can place this radius of gyration here in the numerator down there in the denominator, and we will arrive at this form of our formula. So this is the critical buckling stress formula. We could just express it according to the critical buckling load. Simply divide it by the area if the area is present or not, or if not, then you can also use this formula if all we have is the radius of gyration of our section. All right, so we also have the slenderness ratio over here. That's KL over R, where K is the effective length factor. What about this radius of gyration? I already mentioned this just earlier. And that's equal to R equals square root of I, a moment of inertia, divided by the area of our cross section. All right. Let's now look at the effective lengths of our columns under different end conditions. Okay? So when you say pinned and pinned, that means the end conditions here are pinned. Okay? If we have both ends pinned, then our effective length factor will be equal to 1. K is equal to 1, such that the effective length LE is K times the length, KL, 1 times the length, or simply equal to the length. All right. If our column is in the form of having one end fixed, as what you can see here over at the bottom, and pinned at the top, then our effective length factor is 0.7, and we can now express the effective length as 0.7 times the L. All right, the unbraced length. Okay, what about if our column is fixed at both ends? Then our K is equal to 0.5, and our effective length, KL, is now equal to 0.5 of L. All right, what if our column is fixed on one end and free at the other end? Then our K is equal to 2, all right? And it's as if the column here is simply considering 1/2 of a total column that is free at both ends, such that the total effective length would be 2L, and that's where we have K is equal to 2. So these are the effective lengths of our columns under various end conditions and their corresponding effective length factors as what you can see here down below. Now, let's move on to the NSCP 2001 provisions for structural steel members. In a future video, I will also be discussing NSCP 2015 provisions for structural steel members. Now, NSCP 2001 is a bit old since we're already in 2022, but many universities and colleges in the Philippines still consider the use of NSCP 2001 as part of their discussion on steel design. All right, so how does NSCP 2001 or the National Structural Code of the Philippines consider the analysis and the determination of the allowable stresses for columns? Well, this is the process. The first step is to determine the maximum slenderness ratio of the column, also known as SR maximum. Slenderness ratio maximum, that's equal to KL over R, or the K, effective length factor, L is the unbraced length, and R is the radius of gyration. Second step, we determine the NSCP limiting slenderness ratio separating the elastic and inelastic buckling, and this variable is also known as C sub C or CC, which has the formula square root of 2 pi squared E over Fy. Once you have CC and you have the SR maximum or the maximum slenderness ratio, then here's what we are going to do. We compare SR maximum and CC. Okay? If SR maximum is less than CC, then we determine A. This is just a temporary variable. This is the ratio of the maximum slenderness and the limiting slenderness ratio as defined in our NSCP. Now, once you have this ratio A, we now define the factor of safety. And this factor of safety is Fs, and that's 5/3 plus 3/8 times A minus 1a times a cubed. All right? Now, once you have this factor of safety over here, we now can solve for the allowable stress of the column, and that is equal to Fa equals 1 minus 0.5 of a squared. Once again, a is this ratio over here that we have. All right, quantity multiplied by Fy, the yield strength of our steel, divided by the factor of safety, which we had just solved here in our third bullet point. Now, what happens if our maximum slenderness ratio is greater than Cc? Well, if it's greater than Cc, then the code allows us to solve for the allowable stress of the column directly using the formula that we have over here, and which is just 12 pi squared E over 23 times the maximum slenderness ratio of our column squared. All right. Now, for our next video, we'll be considering an example on how we could apply the principles that we have discussed in this first video. Make sure to watch that other video, the next video after this, so that you will learn on how we can do that. All right, see you then.